So guys, we'll be starting the session soon. In the meanwhile, just letting you know that this session is being recorded and will be posted after the session on the Moodle forum and on the WhatsApp group. Along with that, the slides will be shared and some short notes will be shared too. But regardless, attendance is compulsory for this session. So we hope, in case any of your friends do not know this, please let them know. Uh, you guys do not need to mark attendance anywhere. It will be automatically recorded. So do not worry about that.
Hello guys, how are your vacations going? I hope you'll be enjoying that master ka khana. I'm and I'm also enjoying that me being an H16 student. That's why. So anyways, I'll start the meet. Yeah, right. So I guess you could see my screen now. So hello guys, I'm Daksh Makwana, the convener of Electronics and Robotics Club, and I'll be taking you to the Control Theory Bootcamp at its first webinar, which is what is control. Here we will take you from the very basics to advanced applications of control systems. We'll dive into modeling some dynamic systems and then simulate and tune some real world controllers and apply them to build a self-balancing robot. That's right, guys. And with weekly assignments and then project-based learning, you'll build both intuition and implementation skills. By the end, you'll also earn a certificate, a solid foundation in control theory, plus a real experience with MATLAB, Simulink, and robot simulation. So this is how we'll proceed. So the week one will lay the foundation. It's about understanding what is control and then understanding the feedback and learning some key concepts regarding it. Okay. And then week two will shift to MATLAB and Simulink. where we will simulate and tune some PID and LQR controllers. Then week 3 will be bringing life by stabilizing the self-balancing bot using these controllers. And then week 4 will be more about adding full movement and control logic. So then the bot will be fully functional. And this is what we will be learning in this webinar. Okay, so let's start. First question will arise like, why learn control system? I'd say because it's deeply related to AI. If we get to the highest level of ML, at the core, they are just if input is this, then output that. Otherwise, do some other task. Okay. So control systems, they are almost deep down the same, but better. They are AI, but in the physical world. Not just thinking about a prompt, but acting on it instantly and accurately. Okay. So we'll first understand what really is control and why are they needed. Uh, let's walk through a scenario. Imagine you are in your room and it's really hot. So you walk up to a room cooler and then switch it on. Now it's too fast that the fan of that cooler is making some irritating noises. So you reduce the speed. Then it's too slow. So you increase it. And you do this until you've got that sweet spot in which the room will get cool and you'll get comfortable also. So what's really happening here? You are taking the role of a controller. You sense the current state of how hot is the room. And based on that, you are adjusting the input to the plant using those regulators. And the output, which is airflow, it gets changed accordingly. And this right here, my friends, is a control system. There are processes. So in this control system, there are processes occurring, and then the control systems have one purpose, that is obtaining a desired output with the desired performance given a specific input. Okay. So now that I've walked you through an example also, so can someone give me some examples regarding this whole flip that we talked about? You can raise your hand and unmute your mic. You can also explain like why do you think it is a control system? Did anyone do? No one? Mm,
Daksh, your voice is kind of breaking. You can switch off your video for better
अच्छा
latency. Yeah.
ठीक है so now is
Guys,
it
you can raise your hand if you want to answer. We will unmute you.
so is it right, my voice is it right now? Hello.
Yeah, it's better.
So yes, I was talking about if you can someone like give me examples regarding this analogy. You can raise your hand and we'll unmute you. Okay, then let's do something else. Can you tell me if pancreas, you know, right, what it is? So, like, is pancreas in our human body, is that a control system? If someone will like to answer this question, it will be very nice. Hmm. Okay, I guess then I'll have to answer it. So yes, pancreas is also a kind of control system, and it's because you can think it as it regulates your blood sugar. It basically checks that if the blood sugar in your body is low or high, and it increases it according to that. Okay, so I'll walk you through some more examples regarding it. So example of this control systems can be as simple as driving a car without crashing into anything, as complicated as use of robotics arms for doing surgery, and even the space antennas. like pointing this big antennas towards the farthest distance in the universe with accuracy. It's impossible doing it by hand or even using some simple kind of machinery due to either lack of power or the no compensation for the errors that might occur. Okay. So now that we've got an idea of control, so let's see how to apply it into systems. And we do this by adding a block called controller here. Okay. So this controller will take our output and feed it into the plant. Okay. So I'll walk you through an example for this also. You can think it as a dishwasher. Okay. So what happens is, let's say you want your dishwasher to run for 15 minutes. So the inner circuitries, they will take this input and then convert it into some kind of output, which will be understand by our dishwasher, and it will run for 15 minutes and then clean our dishes. Okay. But now, can someone tell me what could possibly go wrong in this? It can be related to either wastage of energy, okay, or something like that. You can raise your hand and answer this. Like, is this enough? What is the flaw behind the system? I'll just discuss.
Daksh, there are answers in the chat also. You can check them if you want.
Acha. Correct. Correct, Anish. There is no feedback system. If I tell you more simply, it's like this dishwasher will not know if our dishes are cleaned or not. Let's just say that your dishes are cleaned in 5 minutes. So there is then also the dishwasher will run to till 15 minutes. And if the dishes are still dirty, then also there's no way. So what we will do is we can add a kind of sensor. Okay. And this sensor would just check if the dishes are clean right now or not. And we can do this by setting some kind of cleanliness level. And then this will input it into the plant, into the plant and say that into the controller and say that manipulate the time according to it. Okay. So what did I did? I just added a sensor which will check the control variable or the output and feed it back into the controller. Okay. So this is feedback, right? Or by the name guessing, this is also called closed loop system. And the previous example that we talked about, it didn't contain any kind of feedback, so I can uh, told you as open loop system. Now we'll talk about how to control the output exactly by explaining about these controller blocks, okay, and their types. So suppose you get H6 as your hostel, okay, and you want to work from H6 to H15 for secret purposes, and I'll assume that it's 15 meters apart, okay. So here you are. Let's discuss. So this is the diagram we discussed about. You want to work 50 meters, and here you are the plant. Your brain is the controller, and your output variable will be your current location, and the controller will output a walking speed. Okay. Right now you want to walk to 50 meters. So your current location is 0 meters from H6. So it will get inputted into your brain. And one way your brain can possibly think about is getting this subtracted value, that is 50 minus 0, which was your current location. And we'll call it error term. So what your brain can do is multiply this error term into some kind of coefficient. I'll take it as zero point 0.1 and output it as the walking speed. So if I say that 50 minus 0 is 50 and 50 into 0.1 is 5. So initially your walking speed will be what? 5 meters per second. And this is what I have told you about the proportional because it has this coefficient. Now, so as you can see, this is the distance versus time graph. So at first your error will be 50 meters, but it will gradually decrease. And walking speed versus time could be like this. Initially you are at 5 meters per second. So you are walking fast when you're further away, but then you walk slowly and when you're close. So using this, you can kind of reach H15. Okay. But is this enough? Let's talk about a scenario in which it might not be. Okay. So drones. You might be familiar with in the MS-101 we have created these drones. Okay. So let's just say we want to test. So what we want to do is we will fly this drone to 50 meters above the sea level. And for context, I'm defining hovering state, which is nothing, but it's like the propeller, the lift produced by the propeller is equal to the weight which of the drone. Okay, so it will neither go up nor down. And this is that closed loop system of this drone. And here the output will be the current altitude. The controller will be like this, and I take 5 for our comfortableness, and it will output propeller speed. So let's just do this again. Now there can be two cases if I can talk about it. Case one is something like this. Let's just say that your drone has been right now it's above 30 meters above the sea level. So what you might think happened? Let's error is 20 meters, right? And the speed is 100 RPM. The speed will be 100 RPM. So anyone want to guess what will happen after this? You can answer it out in the chat also, or you can raise your hand. As I said, that 100 RPM is what? It's the hovering state, right? So basically, it will just hover. It will get stuck there. The second case might be, let's just say that you increase your coefficient or something, and you are able to reach at that 50-meter wala mark. So what will happen now? Error is 0. Speed is 0. So what will happen now? Yes, it will just get fallen. So what can we do now? I'll say that in the proportional one, we use the present information. That was your current altitude. So how about we use the past information? Okay. So it could be something like this. We introduce the integrator path. So what it will do is, let's just say that you have stuck in this steady state error. So you are getting this steady diagram. So now what will happen is, you know the nature of integrations. So it will just output a increasing value of the propellers. So something like this, we join it with our current controller, and this is integral controller. So now what will happen is, even if you're stuck at the 20 meter wala mark, your speed will get increased. And just like this, by adding and subtracting values, you'll be able to reach the 50-meter mark. But the path that it follows will not be ideal. So why am I saying this? Path should be something like this, okay? So you are at 0 meters, and then gradually you take your time, but you reach the 50-meter altitude. Okay. But I just said something, and it was adding and subtracting values. Subtracting. So this basically means that this is not going to happen. What will happen is, let's just say that you are just about to reach the 50-meter altitude. Okay. So this very small error will indicate that a proportional controller will output almost no value. Okay, but the integrator path, it has been summing up the values since the starting. So here the value of that propeller speed will be definitely more than 100 RPM. So it is not gonna hover. So what it will do is it will go above the 50-meter altitude, create some kind of negative error, which will cause it to decrease its propeller speed. And just by this adding and subtracting values, it will reach the mark and then hover right there. So is there any way that I can even skip this? Like, I just want it to ideally reach or somehow ideally reach. So we've talked about the present, then we've talked about the past. So now it's the time to peek into future. But how? Using the differentiator part. So let's say that your drone is quickly approaching to that 50-meter wala mark. Okay, so uh, that just returns that there is your error is quickly decreasing, and you know the nature of differentiation. When there is a quickly decreasing error, it will generate a negative value. So by this and some joining it with our current in controller set, you will get this kind of a control system. And now the negative value which is generated will act as a brake for the drone, and it will slow the drone down. And now, yes, this is the differential controller, and you have kind of achieved it. So whenever the value of your propeller speed increases and it's really fast, the differentiator will get that, yeah, error is quickly decreasing. So I need to decrease the propeller speed. So these are the three types of controllers. Okay. And if we work with all these three together, we get a PID controller. So now that we have got the types of control systems and then types of controllers, so let's see how to know that what kind of outputs can we expect if we enter any kind of input. And for that, the only way I can think of is use of math. So to first of all represent our system, that is create a mathematical model so that when we enter
Daksh,
the in. Huh?
there's a doubt in the chat. Please answer it.
Okay. Are you asking it for the proportional one? I guess. Okay, okay. So this was the case, right? Hmm. So you wanted to say that why not just increase its proportional value? So let me say this. I'll increase it to 100. Okay. So instead of 5, I'll set it to 100. So what will happen? At 1 meter, it will get stuck. It's just like this. So either you can say that I'll just increase proportional value a lot, but it's kind of impossible to get that much high of a proportional constant value. So that's why we use different kind of thing. So I guess students are discussing among themselves. So no, no.
Yeah,
Yes.
just to clarify that, he was asking why we shouldn't be adding a constant to make it hover there. So what you were mentioning, I think, is that you're adding that constant there. The constant that you're adding there is coming from the integral of the previous values. Yeah, I think it has
So
been clarified. You can move ahead.
yes, yes, the student clarified it. So let's move further. If anyone has any doubts, okay. Sorry. If anyone has any more doubts, you can text it. He or she can text it. Hmm. Chat or not chat. So what you can do is whenever you chat also, no, you can just raise your hand. So I'll get the kind of notification that someone is asking doubt. Is it good? So let me go to the slide. Yes. So I was talking about what so I was talking about now that we have got the types of control systems. Okay, we know what are the types of control systems. Then we also know the types of controllers we have just studied. So now I want to know like what kind of output can I expect if I enter any kind of input. And for that, the only way I can think of is that I use math to first of all represent this system, that is by creating a mathematical model. So that when we enter input in it, it will just give me the output. So I'll start with a system, okay? And this will be the famous spring damper system. So I'll first of all explain you that what is the system here. So this is the block of mass m, and it is attached to a wall with a spring of spring constant k, and then a damper of damper coefficient fv. And we are inputting a force f of t, and we are going to measure it's the displacement of the block, which is x of t. So here is its free body diagram. And yes, just for the context, guys, this is our system. So the block, this whole thing is our plant. The input is f of t again, and the output will be x of t. So yes, no controller here. A kind of open loop system. So by using the NLM, we can just get this kind of differential equation. Okay. This is also kind of a this is also kind of representing the system, I guess. But now I'll start solving it. First, let's just say that I'm gonna input a exponential force and see the displacement of the block. But unlike how to solve it, so can anyone tell me like how can I solve this differential equation? Nice. Yes, you are correct. Using Laplace transform. Because if I use any other method, the ODEs will just get more complicated. Okay, so yes, you're right there. So this man right here, he is Ravi Sebastian, our MA108 prof of previous semester, and he taught us the Laplace transform. So let's just use this. Okay, I Laplace both sides and then took all the initial conditions to zero because they were zero during the explanation of our system. And I just rearrange it somehow, and then we get this kind of algebraic expression. So what did Laplace do is created our differential equations into some kind of algebraic expressions. Okay. So now it's quite easy because any kind of input I input in the system, I'll just take the Laplace of it and then solve it with this function. Okay. So let me generalize what I just did here. So this is the general linear or the differential equation with constant coefficients and it's time invariant. So again, I did the same thing. I Laplace both the sides and took all the initial conditions to zero. And by rearranging it somehow, so here the Laplace of the output is on the numerator side and the Laplace of the input is on the denominator side. So this right here, my guys, is transfer function. So this transfer function, okay. Transfer function is like more than this for me, if I look at it. See, just like we have DNA, which contains different information about us, like the color of our eyes, the color of our skin, or your hair type. Okay, so similarly, transfer function has these terms called zeros of this transfer function P of S and the poles of transfer function, which is the poles of P of S. So what are zeros of P of S? It can be just quite nice. Does anyone want to guess like what can be the zeros of POFS? Yes. Yes, you're correct, Short. Yeah. It's the roots of YFS, that is the numerator. Then poles. I guess poles is also then. Yes. Yes, guys, you're correct. Nice, Durva and Prashant Gautam. So roots of the denominator is equals to zero. That's the poles of PFS. Now, these poles right here, they are a lot more important because these are like literally those safes these kind of saves, which contain so much information about how the system is going to behave. It shapes the system response over time. So now it's time we look for the key which will help us to open the safe. And for that, we need to know a bit of math. So first, let's find the first key. For this, we'll study some standard inputs. So the first is the unit impulse input. Uh, there's this graph, if you can see, and in broader language, if I could say, it's like poking someone a knife or poking someone with a nail or safety pin or something like that. Okay. And then there's in unit step input. This is the important one. And yes, this is the first part of our key, unit step input. It's just a constant magnitude. So it's something like I just flip on a switch. Okay. And then it's unit ramp input. It could be explained as the signal here gradually increases with time. Okay. So now we have got the first part of our key. And for the second part, we look into second order systems. So these are the systems which are like 90% of the physics and the engineering models that we study. And this is the generalized equation for it, the differential equation. So let's do the same here. We'll Laplace it and then take all the initial conditions to zero and then rearrange it and get this transfer function. So now I've got two new coefficients. Okay, so first I can see is this omega n, and then the second is this Greek letter, and this is zeta. So omega n is natural frequency. It can be also explained as how much the system wants to oscillate. And the damping ratio is how much the system wants to resist that oscillation. So you would remember the transfer function for that spring damper system. It was something like this. So can anyone tell me the natural frequency and the damping ratio for this transfer function? You can tell it in the chat. So the transfer function is here. You just need to get it in this form and tell us the natural frequency and the damping ratio of this transfer function. Fy2m. Is it are you answering for natural frequency or damping ratio? Natural frequency is kind of wrong if it is the natural frequency. Root k by m. Yes. Yes. This is like I studied something like this in JE also. So this kind of form. So it kind of refreshed in my mind or gave me nostalgia that oh मैंने ये पढ़ा था पहले भी कहीं. And the damping ratio. बताओ guys बताओ damping ratio. FB by हाँ 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 सही है दोनों का सही है. Nice Srimale, Math Rahul, if I'm pronouncing it right, and Akshay. Nice. So yes, this is the damping ratio. And the damping ratio, this right here, is the second part of our key. So yes, just like Ethan Hunt, in the end, we have got two parts of the key. The first one is quite understandable that input, right? So unit step input. So we'll just input it in the mathematical model and it will do something. But how is damping ratio in second part of your key? We can understand this by just going some in more details. So what will be the poles of the system? Poles of this transfer function? Can anyone text it in the chat or say it in the mic? Because I think testing will require more time. Hmm. बताओ guys, इसका poll. If there's any problem, then poles were, what were the poles? They were the roots of this denominator wala function. Okay, so you just gotta apply the quadratic formula, and you'll get the poles of this transfer function. Mhm. I guess right लिखना सही में बहुत है. Okay, I'll tell you. So yes, these are the poles of the transfer function. And I didn't tell you one thing, right? So it's that the natural frequency and the dampening ratio both will be positive. Why, if I say so, is because I just talked about the physical significance of it. So that just makes sense that for the system to be stable, we need both of these positives. So here you can see some term in the root. So let's just exploit it. So first could be the zero when the zeta is between 0 and 1. So you get the underdamped system. Okay. I'll explain it in the next slide, what are these underdamped in the next, which is zeta equals to 1, and that condition is known as critically damped. And the zeta, which is when the zeta is greater than 1, then it is known as overdamped. So yes, if I look at the graph, I'll start with the when the zeta is greater than 1. So here is the red line here, zeta is equals to 1.5. It represents the greater than 1 wala condition. It is known as overdamped system. And if you can guess why, it's because it's really slow. It is steady. Yes, like it's kind of what we want the system, that is to be steady, but it is really slow. But zeta is equals to 1. That's the critically damped system. And that's the ideal thing. Okay, so that's what we really want to achieve. That is, get the system response win time and stable. So the green line here represents that system. But what we really get, but as I said, zeta is equals to 1 is kind of an ideal situation. Okay, so whenever because gaining that much control is really hard. Most of the time, we end up with either zeta greater than 1 or less than 1. So yes, and finally, the zeta when it is less than 1 but greater than 0, we get something like these oscillations. How do these oscillations come into place? I'll talk about. So now that we've got the two part of our keys, let's uh, input it. But in which system should we input it? See, the zeta is equals to 1, which is the critically damped system. It's ideal one, so I don't think we should input in that system. Then comes zeta greater than 1, really slow and sluggish, right? So I will avoid that one also. So which system is left? Nice. It's underdamped. So what were the poles of this underdamped system? The poles will be imaginary, right? Because it was gray between 0 and 1. So I'll call this part right here, omega n into root of 1 minus zeta squared, as damped natural frequency. So it will be the frequency due to the damping, uh, represented as omega sub b. If I plot these in the complex plane, they would look something like this. And the phase of so this intersection points are the poles, okay? And this phase right here, it makes beta, so cos beta is equals to zeta. Remember this, guys, okay? Just remember this. So let's check this, its unit step in response. That is, let's use our first key. Check input a unit step input. So this is how we calculated the unit step input. Uska Laplace is 1 by s, because unit step input was what? Magnitude of 1. And by rigorous math solving, you will get something like this. Now I know Many are like really sweating or thinking, "हमें ये सब रटना पड़ेगा. We have to just mug it up." So no, you can just think of it as, see here you can see these exponential terms. So they would explain this kind of damping, and these oscillations are due to this sine and cos. You can think of it as like that. And one is our that steady state value or the value that will be finally achieved. Okay. So still the second use the use of that second key, which was what? Zeta is still left, right? So I will use, let's say that I have used that key also. So what will I get is the performance metrics. So they are really the measure of how good is really our system. And these metrics, my friends, is really important. So let me take you to these metrics. Okay. So this was our input. This was a response, I guess. And you can see four terms here, and then this one. So first I'll define a error band. So error band can be defined as plus uh, space between the steady state value, and that can be like either plus minus 5% or 2% or 1%. So that's called an error band. So first is the rise time here, TR. That it is time taken from t is equals to 0 to the time the system response takes to reach its final value for the first time. So final value will be 1. We could guess it by the equation. Okay. So final value will be 1 here. And the peak time, which is TP here, it is the time it takes, the system response takes to reach its maximum value for the first time. And the maximum peak overshoot, this is MP is called maximum peak overshoot. And this metric describes how has the system response jumped from our final value, which is 1. And then the settling time, final thing, the settling time, also called TS. This is the time the system response takes to enter in that error band and never leave that after that. Okay. So you can think of it as when the Pushpa was saying this dialogue, the momentum was increasing in the theaters. And then after that, when he says this dialogue, the overshoot happens. The crowd is like, whoa. Uh, okay. Okay. So I'll quickly describe these metrics. So rise time, the time that a system response takes to reach the 100%. And this could be solved by finding the y of t, wala t, for which that is equals to 1 for the first time. So here is the formula that you finally get after solving. Yes, there's a lot of math, so I'm gonna drop it down. Acha, so can anyone tell me that what will happen if I increase the zeta for this system? You remember the zeta, right? So what will happen to this rise time if I increase the zeta? You can text it in the chat box. बढ़ाओ guys, और बढ़ाओ. क्या हुआ है हर्षवर्धन? Yes, Rahul. Right, you are also right. Anushri, right. Nice guys. सब लोग ध्यान दे रहे हैं इसमें. Everyone is paying attention. So yes, you are right. We can, if anyone didn't get it, why? Then I told you to remember that cos beta was equal to zeta, and this is here is beta. So when we increase the zeta, the rise time also increases with it. Next is the peak time, with the time the system response takes to reach the maximum value for the first time. Okay. So TP, this is the peak time. Not that much interesting, if I would say, but yes, it's important, but not right now in my explanation. Next is maximum peak overshoot. That is how much the system response has increased its value from the steady state value. So the formula for it will be this after solving it again. Ab batao, what will happen when I increase the zeta for this system? What will happen to the maximum peak overshoot? Allow the mark, guys and girls. Nice, nice. Sorry, Saxena. Yes, you are correct in the second time. Gunjan also, Kartikeya also, Rohit also. सब आ गया, सबको आ गया. Everybody should get it. Yes, you're right. So whenever we increase the zeta, the value of zeta, the value of maximum peak overshoot decreases. So can I find any physical significance of it? Let's just say that I am building an automatic door, and it's not like that sliding door. It's like the proper pull push wala door. Okay, so I'm making it automatic. And let's just say that I increase the value of its zeta. Okay, so so what will happen is when the door gets closer to the frame, the maximum peak overshoot or the wobbling of that door will decrease significantly because I've increased the zeta. But what will happen now? It will take a lot of time to reach to that closing frame. Uh, so it will take a lot of time to reach that closing frame. And on the other hand, if I decrease the value of zeta, so the rise time will also decrease, which means that it will reach the closing frame really quickly. But that will also result in the so much hardcore wobbling of that door. Okay, so this is like the hand-in-hand relationship between maximum peak overshoot and the rise time. So yes, zeta, our second key. This is why it's important. So to tweak between these maximum peak overshoots and etc. And final thing, the settling time is the time the system response takes.
कसका लेके चेक काशी ना আছে ওটা সস্তা লাগে थोड़ा আমাকে
Thank you. So settling time is the time taken for the system response to settle within an error band. And we can define it as either plus minus 2% or plus minus 5%. And the formulas will be something like this. So how can I think of it, this settling time? Let's just say that we have got our mattress. If the mattress is highly damaged or it is like really stiff, so I can say that you will not really bounce enough on that bed. But if the bed is if the mattress is really squishy, or you can also say that it's lowly damped or the zeta is really low, then you'll bounce for some time. Okay, so that's the application that I could think of for settling time, and there are a lot of applications as well. So that was my session, guys. Thank you for your the valuable time, and I hope you found something insightful from this session. And now we have got our controllers, now we have got our metrics systems all ready. So what are you gonna do in the week 2 is use these metric systems, use these metrics to, tune your controllers, because there will be some error. क्योंकि error के बिना जिंदगी थोड़ी चलती. So thanks, guys. If anyone has any doubts, they could say it right now, or they could DM me personally. Have I attached my number? Yes, I have attached my number. So you could just WhatsApp me in this on this number, and I will reach to you as quickly as possible. There will be also we will also provide a booklet within 2 hours or something. So that will include all these topics and some more if you want to research more about it. Like let's just say that I talked about poles of the system. If you want to discuss some study some more about that, you could do it using the booklet, or we will also upload the resources also. So thanks, guys.
Guys, since this was the first session, anyone with an attendance time of 30 minutes or more will be given full marks for attendance, but it will be different from next week. As Daksh mentioned, the recordings, the notes and the slides will be shared within 2 hours. And by end of the day today, you will receive the first week's assignment, and we will be expecting you to submit it before the next webinar.
हाँ रुद्र, did you raise your hand? रुद्र खंडेरी वाला, I guess.
It's all good. It's all good. गलती से.
अच्छा अच्छा. हाँ, here Anushri. She disconnected. Thank you guys. मैं आपके चेहरे नहीं देख पाया. I couldn't see your faces, but it was really nice that I could give my first webinar to you. You were really intelligent.